Hi, everybody. And let's get started tonight. So, thanks everyone for coming. I'll just do a quick land acknowledgement and introductions, and we'll get started. So, the Berkeley Public Library acknowledges that we sit on indigenous and unceded traditional lands of the Chochenyo-speaking Ohlone peoples. We honor with gratitude the land itself, as well as the Ohlone peoples who still live, work, and play in this region. Our library also does a monthly event with Cafe Ohlone. That's happening tomorrow on Zoom. They're playing an Ohlone game with sticks and crafts. And I think that starts at 6 p.m. if you're interested. So, Talking to Science Bubble, one of my favorite programs. This is a monthly seminar series that aims to share new research findings from graduate students and postdocs at UC Berkeley with the general public and create constructive discussion about a variety of science topics. We have 2 speakers at each seminar who will talk about their current research or a topic that we find really interesting. The organizers are 4 graduate students at UC Berkeley, Taylor Zung, Daniel Bredhauer, Madison Lemur, and Oksana Ondrik. Madison and Oksana aren't here tonight, but Daniel and Kaylin are. Lectures always happen on the 3rd Tuesday of the month at 5:30 p.m. down here. The programs are archived on the Science Bubble YouTube page, so you can view them later and share them with others. Talking the Science Bubble also has a website and a listserv that you can join to keep up to date with new Science Bubble lecture topics. So I'm going to let our organizers introduce tonight's speaker. Thank you.
Hi, everyone, and also friends on the Zoom land. So first, thank you all for being here, and thanks to our speakers tonight. As Kelsey said, we host a talk the 3rd Tuesday of every month, and we have researchers from a wide variety of departments. So if you're interested in learning more about our future talks, seminars, please join our QR code that is, or our listserv that you can find through the QR code, and also via our website and YouTube channels where you can find the previous recordings. So for tonight, we are excited to have Joe and Rajiv with us to present. This is an open format talk, so we encourage questions throughout the presentation. You can submit your questions either through the chat function or Q&A on Zoom, or you can ask in real time with your hands up. We will also have time after each talk for more questions as well. So to start us off, tonight's first speaker is Joe Brackbill. Joe grew up in Wyoming, Pennsylvania. He attended Dartmouth College in New Hampshire, where he enjoyed his many hours rowing on the Connecticut River. Now a graduate level chemist in the group of John Arnold at UC Berkeley, Joe tries his best to take advantage of California's beauty by hiking, running, and skiing when not in class. So let's welcome Joe.
Thank you for that introduction.
While Rajiv is getting everything set up. So Rajiv is a postdoctoral fellow in the group of Professor Joel Ager at Lawrence Berkeley National Laboratory. He obtained his PhD from the University of Zurich under Professor David Tilley. He has an undergraduate degree in physics from the National University of Singapore and a master's in materials science and engineering from Nanyang Technical University. His research interests are investigating photocathodes for CO2 reduction and understanding its reaction mechanism for carbon-carbon coupled products. So without further ado, we can take it over.
Thank you. Thank you very much for the introduction. And yeah, I'm very happy to be here. I think this is the first time I'm coming to the library. I'm always up the hill. So I'm from Lawrence Berkeley National Lab, as you can see. Promotion for the National Lab over there. I hope you saw the movie Oppenheimer. Yes. Radiation lab, which is called there, which is actually Lawrence Berkeley National Lab right now. And why do I have all these things? And the first slide is because I have to acknowledge who is funding me. It is a program called the Liquid Sunlight Alliance. It's a conglomeration of many different universities from LBL, UC Berkeley, Caltech, NREL. NREL is actually National Renewable Energy Laboratory, and also UC San Diego and UCRY. Okay, so let's go into the topic today, which is fuels from sunlight. I just want to make sure that
I think you're sharing the wrong part to Zoom.
oh, in Zoom, I'm sharing the wrong screen.
We're seeing like all of your slides.
Oh, all of the slides. Oh, okay. Is this the right one? Okay, excellent. Yeah, that was my next question was going to be, is everything okay on Zoom? Like, can the audience hear me? And okay. So a little bit about myself. So I studied physics and material science at Nanyang Technological University in Singapore. This is Singapore. This is the Marina Bay Sands. A very nice view from the top over there. So I would definitely recommend if you have a chance to visit Singapore. Not only there's good science over there, good tourism also. And then I went to the beautiful Alps to do my, I didn't actually do my, I wish I did my PhD in the photo which I showed share over there, but I did not. I did it at University of Zurich. It's not as beautiful as that one. This is the top of Europe, basically in Switzerland, where I studied chemistry. And then after that, I came over to Florence Berkeley National Lab to do my postdoctoral research. So a little bit about our group. So this is my supervisor, Professor Joel Ager, and they're just celebrating publication of a paper recently. So, and some fun activities we do at the group, some Christmas events at the Berkeley Material Science organizes some Christmas parties, and we also do some fun science at the synchrotron, which is actually, what is the synchrotron? It's actually this. Whenever you see a picture of the Berkeley lab, every Zoom background, every background we show is the synchrotron because it's a very nice view over there. So yeah, now.
If you go to more on the far right there,
Yeah.
and then hide floating meeting,
Thank you.
and you can also X out of the.
It's right exactly at the wrong location. Thanks, yeah. Thank you. So what is the scientific motivation for all of my research? It's straightforward. Yes, climate change is the main motivation for my research. And we don't want to have a scorched earth. As I feel like it's very easy to motivate because most of the people are aware about it, given all these wildfires we see every year, record temperatures going. Okay, now I'm trying to convert from Celsius to Fahrenheit because we use both. Okay, like, yeah, 130 Fahrenheit is considered as 55 degrees Celsius or something. There's some places in Earth that go so hot. So that's why we need certain solutions to address climate change. So what can we do with CO2? Okay. Any suggestions? Yes. Turn it into water. Huh? You can turn it into water. I'm going to be using water also, as I will show you. Yeah, thank you. Yeah.
Can you explain this to that? Our industrial processes?
There is one startup company which is actually trying to do exactly that in the Bay Area. So that's an excellent idea.
Capture it in plants.
Plants are the best for us. Yes, exactly. We need to plant more trees.
Not of soda.
Fans of Coke and Pepsi. Yes. Actually, the solubility of CO2 in water is actually a key factor in my research, but I'm not going to go into detail in that, but that's very important also. Like, oh, sorry. Yeah, okay. Okay. So what do I do with that? So I use CO2 to try to convert it into fuels using sun and water. That's the crux of the story. CO2 to fuels. Basically, we take all the CO2 emissions that we make, we can capture it. So I'll explain a bit more what is this photocathode in a moment. We can use sunlight and water, convert CO2, make fuels and chemicals, and then we can do it in a circular economy. That's the bigger picture. I'm not there yet. That's why I'm doing the research. So what's the science behind? I'll just go a little bit technical here. So you absorb, not you absorb. I make materials which can absorb sunlight, which is this nice yellow arrow over here. And you make electrons and holes. Let's say you make this. And these electrons over here, which you see here, can convert CO2 into certain products. So, okay, the science looks, oh, we can do that, right? But if we can do that easily, I will not be here. I won't have a job at Berkeley National Lab. It's because we can do that, but the process is not very efficient. So you have, let's say, 100 photons from sunlight coming in. Not everything gets converted into a useful fuel. It just some becomes something else, another part of it brings up something else. So this is what we call product selectivity, which means we don't make something useful very selectively. It's like, I want to make this, and you have to make this, but we don't do that. We make a bunch of different materials. So my goal is try to investigate the fundamental reaction mechanisms. So only from the fundamental research, when we do basic science, only then can we go into much more applied. So I use the material which is there in every cell phone and in laptops, silicon, and another abundant material. We have to be very lucky to have found this material because this is like the workhorse for all the catalysis, all the CO2 to fuels, which is copper. It's cheap, abundant, it's there in many of the wires that are running around. So it's not like a costly, expensive, like gold or silver or something like platinum that we need to worry about. So how does a typical week in my life look like? I make these materials, these photocathodes, which absorb sunlight, make electrons, and they convert in CO2 into fuels. And I have many different tricks that I have to employ to try to improve its efficiency towards making a high concentration of the product, and then analyze the product. You make your material, put the catalyst, do some like nanostructure it. There are certain other things which I can go into detail if needed, and use the analytical chemistry tools that we have at the lab. See if I improve this efficiency. It's terrible. Most of the days it's terrible. So I got to repeat the same thing, change certain parts of the catalyst in certain aspects of it. And again, earth abundant material, silicon, cheap catalyst, copper. So that's where fundamental science, and also I should think a little bit about if I had to make a reactor for our, let's say you want to put a reactor outside Berkeley, and which can convert CO2 into fuels. I cannot say I'll make something with like platinum or uranium, something that's very, very expensive and precious. So motivation is cheap, earth abundant catalyst, which can be fabricated easily. Silicon, I know we can all make it easily, otherwise it won't be in any of your phones or in your laptops. So another bigger vision would be that, so you have your photocathode, so shine light onto it, you make these electrons and holes, electrons convert to CO2, we can make some fuels, methanol, butanol, ethylene. This process is called CO2 reduction. So if there is a reduction reaction, there must also be a counter oxidation reaction. And usually what happens is water gets oxidized and it makes oxygen. Oxygen, of course, is very good. This is how actually in submarines, they make oxygen for the sailors is they do water electrolysis. So they apply a current to water after removing all the salt, and that makes an oxygen, and that's what is actually helping the sailors in the submarine for their oxygen supply, because yeah, of course they cannot come out and breathe. So instead of doing that oxidation reaction, we will do a certain oxidation reaction called HMF, but I will not go too much into detail about that. But like, it's basically a material which you can derive from biomass. So biomass that's just lying around, you can convert that. You get HMF from that, and if you do oxidation, you can actually make this thing called FDCA, which is actually a precursor for making bioplastics. So all our plastic materials, we can fully make bioplastics by this process. So the full picture, this is the ultimate vision would be reduction, oxidation. You make sunlight, CO2, and water. These are your inputs. And then, so, okay, and also I just want to describe how is the work atmosphere that I'm currently using. It's not like just alone, just myself, not by myself, doing experiments. As I mentioned, I'm part of this Liquid Sunlight Alliance program, which is that's why it has to be a collective effort. One person cannot solve this. It's a big problem. The Department of Energy realizes this. So that's why they're bringing all the scientists from across the US together, at least, with this Liquid Sunlight program. We have this National Renewable Energy Laboratory and also Caltech. So every day it's not every, sorry, every week, or at least in a bi-weekly basis, we constantly have interaction of different research with different scientists from all these different institutions. So it's just not, you're just not in a bubble, I would say. But I was like, then I was thinking, oh, we're popping the science bubble, but yeah, that came into my mind. Yeah, so like, yeah, so that we are not just in one bubble thinking in one dimension. So when you interact with different minds, different ideas, that's where we can make real change. So what I hope to achieve through my research career is, yeah, I'm just a small person making small steps towards climate change. So every single contribution to science matters. So that's why I'm trying to do as much outreach as I can to as many people as possible. And yeah, it definitely takes the efforts of the entire community, not just the scientific community, that every person can help to contribute in any small way would be nice. And the satisfaction which I gain, like why I get 90% of the results that I do is failure, but the only satisfaction I do that with one small, that okay, maybe 95 is also over underestimating it. 99.99% is failure, but that 0.1%, you have to find that hit. Once you find that, then it's fine. Then you can just go with it. So that's why the only satisfaction that gives, okay, until I find that, it's going to make a good, important difference. Also, I enjoy mentoring scientists, like from all stages of life. Like I had people who just came out of high school working in the lab. I even had people who are more senior to me, and I trained them on some experiments also. So every stage of the career, we can learn, we can all make it better. And with that, I would like to conclude, and yeah, I'm happy to answer the questions.
So with, you mentioned that, you know, it's still trial and error, but with what you're trying to achieve, is your definition of success something that oil and gas companies would love to integrate in what they do, or are you going to be like an enemy of them? You know,
I see. I'm not sure if I'm going to be in direct conflict with them. If I can actually, not if I can, if we can actually, like, you know, they produce tons of CO2, of course.
Yeah.
And if I can make a case for them, hey, all those waste that you throw away, I'm going to make something useful for you. Like if I can make methanol, I make a fuel for you.
Mhm.
And they're going to be like, yeah, come on over. But yeah, I mean, that we don't need to be like against, there is some, ideally we can work together also. I mean, I mean, they're motivated by profits. Yeah. So if I have to make an economical argument, if I have to work with us, like, so you're wasting those things, let's not waste it, we'll make something useful out of it. So that at least the CO2 doesn't go into the atmosphere. So I think there was a hand over there before, so sorry, yeah.
I was gonna ask, the carbon capturing plants that opened up in early 2019 in places like Philadelphia and North Carolina and stuff.
Mm.
Would this actually help them improve to actually grab more carbon out of the atmosphere?
Mm. So I mean, it won't help them to grab more. It will only help them to convert it. Yeah,
Oh,
so they are gonna capture. So it's just what they do is they capture and then they store it somewhere else.
yeah, they have.
Yes,
They're ready.
yes, exactly. So instead of sitting there, we will we'll make something useful out of it. That's, so there is a carbon capture and there's a CO2 utilization. Parts of it, like two parts of the. I think there's a question here.
Yeah, thank you. That was very interesting.
Mhm.
What you're doing, and also thanks for showing, the struggles that we all go through.
Yeah.
90%, that sounds all right, yeah.
Mhm.
Anyways, yeah, I was wondering, like, so you have your fuels, but I guess they also produce residuals,
Yes.
and then does it ever get carbon negative, or you get carbon neutral, or you get carbon positive? And on that note, how would you compete with something which is like 100% carbon or like carbon negative, like electric and other, like, what is the place for this type of fuel in the market of renewables?
It's going to be mostly carbon neutral rather than carbon negative, because we are not taking, or maybe we can actually, I mean, because capture is another side of the equation and we are not in that part of it. Like, so for it to be negative, we got to be pulling more CO2 than what we are putting in.
I don't know,
But
but could you like convert into something else that doesn't have the same properties?
Yeah.
Or...
So that's what we are trying to look at. So the argument that we can make is we can make fuels or chemicals, which usually you make with fossil fuels. If we can replace that process with the CO2, so that would actually be somewhat negative, you can say, because like if you make ethylene, polyethylene, or those kind of products, which is like you make from petroleum-based processes right now. So if you say, okay, we can completely replace that with a non-petroleum-based one, there can be some economic benefit and also benefit for the planet. Yeah. So, did I answer all the questions?
Yeah, you can see like a place for that in the context of renewable energies that are already like available and getting very cheap on it. Could you see like a place for this type of fuel, or
like, for example, we can, you mean a place in where?
like
Like
the market, like
the market, okay.
yeah, because we have already all these options, and then these are actually helping, replacing the CO2, or like what causes CO2 emissions, right?
So the ideal goal would be to have this circular economy. You make your fuels from the CO2 that you put in, and then it goes like without you adding more CO2. Like if you keep burning more and more fossil fuels, we're like adding more and more into the atmosphere. But now the argument would be we take CO2, use the same CO2, fuels, goes out, comes back.
What if you make the circle smaller?
We can always do better. We can always do better. Yes. But the technology is at its infancy right now, so it might be a while before. There is good amount of investment into it, scientific and from industry a little bit. We do have actually a startup which came out of our building where we are working. So they are actually doing CO2 reduction. It's called 12 carbon is 12, so like companies name it 12, and they try to like convert CO2 into CO, carbon monoxide and hydrogen, and you can use that as a precursor towards making other chemicals.
I was gonna ask a related question.
Yeah.
About like, with the kinds of fuels that you are able to make from the captured carbon, when you use them, they also emit carbon. So the argument is, and I guess I was just wondering, since emissions are, different depending on which chemical or which fuel you're using, is there like an efficiency loss to where at some point you're still leaching carbon into the, like, you're not gonna perfectly capture it all?
Yeah, it's not gonna be 100%.
Yeah.
So yeah, fuels and chemicals ideally would be the way to go. If I can, for example, the other oxidation, like the oxidation reaction that they showed there, if you can make plastics, biodegradable plastic, we basically completely replace, or not completely replace, like slowly phase out the other petroleum based. I mean, it's not going to be super fast. Yeah, it's gonna be like small steps. Yes.
How close is technology today to what you would want for carbon capture for this to work perfect?
Okay. With carbon capture, we have made incredible strides in carbon capture. It's right now, it's not 100%. I mean, it can capture to its best, it can, but it's still energy intensive process, the carbon capture. There are certain companies called Climeworks, like have like huge fans and then blow through that through like a hydroxide solution, and then it makes a carbonate of it. So CO2 bubble through a hydroxide solution, then you make a carbonate, and that's how it's basically stored there. So that's carbon capture. And interestingly, I use carbonate solutions, and then I saturate that with CO2 to do all my experiments. So it could be integrated with that, but that's a much bigger problem than what I'm focusing on. Yeah. Oh yeah. Yeah, go. Yeah.
Okay, it's interesting, like when you are doing your work, what do you change? Like you use silicon and copper, what do you actually do to make it more efficient? And what's your matrix of measuring it? Like, do you change the cathode structure or the composition, and then how do you do it?
Yes, exactly. Thank you. So now we can go a little bit more into the science. So this silicon, which I use, which is absorbing the light. Right now I'm using like a flat silicon. We can actually make it nanostructured, then it will absorb much more light. And you can increase the figure of merit is called Faraday efficiency, which is like how much electrons are going towards making the product that you want to make. Like, let's say I want to make ethanol, and it's not going to be 100% Faraday efficiency, so it's going to be like 10%. I'm just giving you a number. And then, so how do we improve that number, improve the Faraday efficiency? You can play with a catalyst. Sometimes people add other metals to copper to make a bimetallic catalyst. That improves the performance a little bit. Like if you have copper and a little bit of silver, it improves the performance. So you add a tiny bit of silver. So that's one trick that we can use. And also with how the catalyst is supported on the silicon. There are different layers that one could explore. Some oxide materials. That's one part of my research also. Figure of merit, push the Faraday efficiency to 100% to whatever product that you want to make. You want to make methanol, you want 100% methanol.
100% means that every single sunlight, every
single electron is going to making every single electron is going to convert CO2 into methanol or any product.
So that's a theoretical limit.
I mean, that's the maximum, but I'm prepared for 60-70% also to see. Right now, actually, we can even make like 50-60% ethylene with high efficiency. This is over the past 10 years of research from, like in the 90s, nobody was even doing this. There were many scientists who were telling that it's possible, but nobody was investing any resources or effort into it. Only in the past 10 years, the efforts have gone much more intense. So there's a question here, yeah.
So kind of going off that question, using 60% of electrons, and we want to get it into the marketplace like a fossil fuel company. I'm thinking tangibly, would we need like fields and fields of solar panels with this, with the silicon or whatever? Like what is the scope of infrastructure that would need to be built to go from the carbon dioxide to the fuel?
Yes, thank you. So that's why we are trying to use silicon, because we have already a large manufacturing base for silicon, whether it's the photovoltaics or the semiconductor industry, chip makers. So we can actually make even large panels of silicon without any problem, and we can design reactors along those sides. And with regards to how much land mass or area that we might require, I don't have the numbers on that. So I mean, I really, but it is big, but you make a lot of, the larger it is, the more products that you make. Even if your efficiency goes down a little bit, you're gonna mass produce a ton of methanol, or for example, yeah. So we can actually even, I mean, I'm not sure if you're familiar with concentrators, light concentrators. So there's this big mirrors, which, let's say, oh yeah, actually the setup is nice. This is a setup. This is your light absorber. There's like a big mirror over here, like focuses all the sunlight towards that. Makes super highly efficient, because you have much, well, you have like 20 suns falling on one piece of silicon reactor over there. That can make, for making electricity, the infrastructure is already there. So if we can, that's why we want to use something is already there. And then if we can integrate the catalysis onto that light absorber, then we can do fuel production or chemical production. Yes.
Are there different materials people are using, different research groups doing the stem out and using different materials, catalyst or silicon replacement?
Yeah, like silicon is the kind of best for the light absorbing materials, you know, is very good at that. For catalyst, copper is the big one right now, because other metals, they don't make chemicals more efficiently. So there is some research trying to use different catalysts. So you can make one product here, and you can make another product here, and these two can react together to make a third product. There's another branch, or there's other research directions which focus on that. We call it cascade catalysis.
Let's thank our speaker again. We'll stop out.
Yeah. So did you send it to my email? Yes. Yeah. Oh, it's quite big. Oh, yeah. Is it the correct one? Yeah. This again, let me make sure I share it on Zoom. The right one. Is it okay?
It's loading.
And then you have
Yes.
to fix the topic.
Oh, yeah.
So go to more.
Perfect. All right, many thanks, Rajiv, for lending your laptop and for a great talk.
Thank you for your patience with the technical challenges. I don't know how it can work and whatnot, but that's science, I guess. So yeah, my name is Joe. I'm in John Arnold's group at UC Berkeley. So I'm in the Department of Chemistry. We do actinide and transition metal chemistry in John's group. And today I'm going to be talking a little bit about my work, but trying to set it in a bigger context of uranium's history, the specific challenges that we face with this element, what its potentials are, and then yeah, try to work my my own research in a logical way. So as was said earlier, please interrupt with any questions that you have. If I use some jargon accidentally that really throws you off, please just raise your hand and I'll try to verify it. So just some intro stuff on uranium itself. So this is the periodic table of the elements. Hopefully looks familiar from some point in your education. The elements get heavier going to the right than going down. Uranium is all the way down here at elements 92. It's the heaviest naturally occurring element. So there are heavier elements like neptunium and plutonium, for example, at 93, 94. There are also the super heavies, things that are, synthesized, for example, at cyclotrons. Some of these have been discovered here, like berkelium and californium, right in Berkeley. So that's all cool stuff. But uranium is the heaviest naturally occurring. It's a relatively hard, silvery gray metal. You can actually apparently buy it from this website if you're interested. Ampules. But this is not how you find it in nature. When you find uranium in nature, it looks a whole lot more like that stuff. Because like any electropositive metal, uranium is found as some mixture of minerals. So you don't just go out and find, iron metal in nature very frequently. You find rust, basically, and then you have to make the metal from that. So we encounter uranium in these different minerals, and it can be mined a number of different ways. It can be strip mined essentially, or leached, or things like that. It's actually not a very rare element. So it's, I think, the 50 or 51st most abundant element of the natural elements. So about 40 times more abundant than silver, something like 200 times more abundant than gold. We have a decent amount of it. It's rich in places like Kazakhstan and Canada and Australia in particular. Whoops. Break the clip. And here's where things are going to get a little sciencey, but uranium, when you encounter it in nature, is found in two primary isotopes. So an isotope of an element has the same number of protons and electrons as other isotopes of the same element, but it has a different number of neutrons. So the specific atom is heavier or lighter, but it exhibits the same chemistry. So uranium is found in two primary isotopes, 238 and 235. So what that means is they both have 92 protons and 92 electrons, but uranium-238 has 146 neutrons. 235 has 143 neutrons. So the difference in the number of neutrons has no impact on their chemistry whatsoever, not appreciably, but it does have an impact on their nuclear physics. And that's where the whole story of uranium really begins. So uranium-238 has a half-life of 4.5 billion years. That means every 4.5 billion years, if you have 1 gram of uranium at the start, by the end, you'll have half a gram. So you lose half of it over that half-life. So that's conveniently actually about the age of the Earth, and uranium is useful in dating things. And this is the vast majority of natural uranium in nature. It's about 99.3%, and it's non-fissile. We'll get to that in a second. Uranium-235 has a half-life of about 700 million years. So it's a little bit shorter than that of 238, but not that much actually. It's a small percentage of natural uranium, less than 1%, and it's fissile. So fissile means that if a nucleus is fissile, that means that you can hit it with a neutron and it will undergo a fission event that is self-sustaining. So in this chart here, you can see that this is from Wikipedia. So a neutron hits this 235 uranium nucleus. It absorbs that neutron to form a very unstable uranium-236 nucleus, which then undergoes fission. this is really sort of a simplified schematic. These are not the only two products you get. You get an enormous mess of products out of this reaction, but you get more neutrons out, and those neutrons carry on the chain reaction, leading to a critical event. So if you have enough uranium all bunched together, it can reach criticality, at which point it generates an enormous amount of energy. So that's what this chart is really missing, is that in addition to splitting that nucleus, you get a huge amount of energy out. So this can lead to a lot of good things. So here is a chart of the nuclear fuel cycle. Nuclear fuel accounts for about 20% of worldwide power generation, and its forecasts think that that's probably going to stay pretty stable over the next 10 years. Even in the US, we rely about 20% on nuclear fuel. It's a carbon-free process in that when you're actually burning the fuel, you are at no point emitting carbon dioxide. So many people have made the case that in the current climate crisis, where we are pumping a whole lot of CO2 into the atmosphere, nuclear fuel could help bridge the gap between our current petroleum-heavy energy generation industry and the renewable energy industry of the future, by doing something that's carbon-free. It's not fully carbon-free because the different parts of the process are not carbon-free, the mining, the milling, etc. But overall, it is orders of magnitude more efficient than, for example, burning coal. It's also actually a really important source of medical and industrial isotopes. So if you ever are in the hospital and are unfortunate enough to need some sort of radioisotope injected, there's a chance that came from the nuclear fuel cycle. So here I'm showing this beautiful yellow cake product that is milled. I'm not going to get into this cycle. If you have any questions about it, I'd be happy to share what I know. But of course, probably we all know that the same reason that uranium has constructive potential, it also has extremely destructive potential. So in 1945, the US dropped the first and the last weapons that were detonated on planet Earth in a wartime event. The Little Boy and Fat Man weapons, and this began the nuclear proliferation cascade that really was sort of the crux of the Cold War between the USSR and the US. So in the 60s, 70s, etc., we saw a lot of nuclear proliferation, which means we saw many more weapons being developed. We talk about both vertical proliferation, so that's one nuclear state making bigger bombs, which we certainly did, and horizontal proliferation, which is new states making bombs. So we've seen a lot of examples of this over the course of history. For example, vertical proliferation in the US, the Little Boy was a 15 kiloton weapon. So the US Department of Defense measures the yield of a weapon in tons of TNT. So the Little Boy had an explosive effect similar to dropping 15 kilotons of TNT. But the biggest weapon we tested was at Castle Bravo, which that's a little GIF of that going off there, which is 15 megatons. So that's 1,000 times the power of the Little Boy. Yes?
Was there?
Yes, it was. Yeah, that was at Bikini. One of the biggest radiological disasters on Earth. The US is still cleaning up that mess, and reparations are ongoing for the irreparable damage really that was done to that area and the indigenous people there. So just to give you a sense of scale, the mother of all bombs is the largest conventional weapon that the US has, and I believe has ever had, similar to the Daisy Cutter that was used in Vietnam. That's 11 tons of TNT. The Castle Bravo test was 15 megatons. So that's just doing some, back of the hand math. Castle Bravo was about 1 million MOABs, all going off at once in the same location. Just incredible power. It was only supposed to be 7 megatons. There was an egregious error in estimating the power of that weapon, which is why it ended up being such an enormous disaster. So yeah, we are aware that nuclear weapons cause an immense amount of damage. Unfortunately, that's not all the bad news. Both good and bad applications of uranium or other radioisotopes yield nuclear waste. So what I'm showing here, this is actually the isotopic distribution that is yielded from the thermal neutron fission of uranium-235. So after you you burn your nuclear fuel. What you end up with is this huge mess of elements that spans the periodic table. You have cadmium, strontium, all kinds of junk in there. And unfortunately, you don't only get lighter elements, you also get heavier elements through neutron uptake, beta decay. This transmutation chart over here shows how you can climb up the periodic table from plutonium all the way up to americium, to curium, to californium, and beyond. And all of these elements make this gnarly stew that's really difficult to deal with. Separations are expensive, and this is a proliferation concern because you can have a state say, hey, I just have uranium. I'm just going to burn uranium for peaceful purposes to make energy for my state. But actually, a huge amount of the energy that comes out of the uranium reactor is coming from plutonium that's generated during that process. And you can get plutonium very easily out of spent uranium fuel. Pretty much no matter what fuel you use, there's some way that you could potentially weaponize the waste. So it's a real concern. So where does chemistry come into all of this? The way I see it, there are sort of two focuses in uranium chemistry, two general aims that the community has. I would say that focus one is how do we steward nuclear power generally? How do we handle the mess that we make when we burn fuel? How do we handle all the weapons that we have, all those thousands of plutonium pits that we don't know what to do with? And here I'm showing this sort of simple organic structure. Here's some chemical acronym for it to represent this focus area, which this chelator is, this molecule is being investigated as part of nuclear waste separations to help improve those separation efficiencies so that we're dealing with less high-level nuclear waste in the long term. So there's a lot of active research, and this, this is certainly not the only area that's being investigated. People are investigating how to make more, efficient fuel pellets, how to make separations more efficient, how to steward the plutonium pits we have better. There's a huge amount of research that goes in this area. I'd say the other main thrust is how do we expand the usefulness of uranium? Because this is an element that we really just haven't studied that much, and it could actually do productive chemistry for us in with completely different areas of life. So to illustrate this, if the chemistry of iron is as old as these old iron coins from like 3,000 years ago, then the chemistry of uranium is like this baby that's just waking up. So this element was only isolated a little over 100 years ago. It can do a lot of cool stuff, but we haven't really studied it for that purpose yet. We've really been so focused on the nuclear physics that there's a lot of potential applications that we haven't explored. So to demonstrate this sort of second focus, I'd like to highlight the work of Rebecca Abergel, who is a staff scientist at LBL. She's also joint nuclear engineering faculty at UC Berkeley. So she works right up the hill. And her group does some really cool work to address a couple of different ways that we could expand the usefulness of uranium or sort of address some of the problems that we have with handling this element. So one is designing these fancy organic molecules over there for decorporation of uranium and other radionuclides from the body. So if a worker at a nuclear power plant is somehow exposed to this, how do you get it out of them so fast that there's no harm done to them? So that chelator is being investigated as one way of decorporating that. Another is bioconjugation for targeted cancer treatment. So this big purple or pink blob thing is meant to demonstrate some sort of targeting entity that you could use to actually inject a radionuclide intentionally, into a patient to target that to cancer cells and basically hit them with very focused radiation. So you don't have to, hit the whole person with some potentially damaging radioactive scheme. So her work is really cool. I think it shows that there are both hazards associated with these elements, things we need to get out of people, and ways that we could use them to combat totally different problems like cancer. So in my work, I have had the honor, I think, of doing a little bit of work sort of in both of these two focuses. I've done some work on what I would call sort of the stewardship branch at the ALS. So like Rajiv talked about, there's a big round dome structure up the hill This thing shoots really, really brilliant light, very highly intense light that we can use to study materials in advanced ways. And using that, the team I'm a part of tries to identify where things like spent fuel or, fuel that shows up where it's not supposed to, or weapons grade material shows up that it's not supposed to, where that stuff came from, what it's made of, because by identifying what's in there, you might be able to figure out, okay, is this from Kazakhstan, is this from Russia, et cetera, et cetera. And then the second focus, and really what I built my PhD on, is the development of new chemicals to just try to broaden the chemistry of this element, the fundamental chemistry. I think this is supposed to, spin or something. This is just classic chemistry. I have my flask. That's a uranium compound in there, starting. It's a really beautiful dark green color. I love to study uranium because this thing can span the entire range of colors of our beautiful deep blues and purples to light yellows. It's great. So then what do some of my results look like? This data wasn't collected by me. I don't know if I can show you the data I've collected or not, but this is an example of one of the sorts of spectra that we would get out of the ALS. So you can see here that our team was able to identify lines in this spectrum that are characteristic of uranium, which is not surprising. We have uranium in this fuel pellet, but then we also are able to identify other elements like barium in there that maybe are an artifact of the production process. We might be able to use that in conjunction with other evidence to figure out where this thing was made and stuff like that. So this is part of the stewardship program. How do we make sure things aren't showing up where they're not supposed to be, et cetera? And then the development, I'm looking for new interactions between uranium and elements like silicon or gases like hydrogen. And this here is a crystal structure of one of the compounds I've made. So you can see the uranium is bound to the silicon center in this structure. This is using a technique known as X-ray diffraction to actually basically visualize where the atoms are in three-dimensional space. It's a very cool technique. So at this point, you might be wondering, wait a minute, uranium is radioactive. How can you work with it? How do you need to work with it? So I thought it might be helpful to go through some sort of myths about radiation and uranium in general. So myth number one, radiation is avoidable. I think a lot of people actually believe this, but you can't avoid radiation. We're constantly exposed to it through things like cosmic rays, just being on planet Earth, as well as naturally occurring radioisotopes. So radium that's in the air. There is just, as I already said, actually a decent amount of uranium just in nature. So there's going to be at any point in time uranium in your body. As well as, potassium-40, you might have heard about the banana equivalent dose. Whenever you eat a banana or whenever you eat a potato, you're getting some amount of radioactive potassium in you. That's fine. Your body can handle low levels of radioactive events. That's really not an issue. Another myth, uranium is highly radioactive. It's actually a very low level alpha emitter. So what this means, the fact that it's a low level emitter means that it has a long half-life with a low decay rate. So compared to something like plutonium, which has a half-life many orders of magnitude shorter, uranium is decaying much slower. So your, radiological damage is always going to be a question of exposure over time. How much were you exposed to over how much time? So you would have to be sitting next to a lot of uranium for a long time to really increase your risk of anything bad happening. And then the fact that it's an alpha emitter, an alpha particle is a specific type of radiation, they're very easily shielded technically. So just in my reaction flask, that the radiation escaping the flask is no longer appreciable. You can't detect it. So, and even actually just a few centimeters of air are really enough in a lot of cases. So these alpha particles are easily shielded, so there's very little risk to me. I still take, of course, great precautions not to ingest it, which is sort of a different problem, but I don't eat the things that I made, unlike the chemists of old. And so I'm generally fine, at least for now. And then another myth that I think can undermine some potential applications of the radioactive elements is this idea that exposure to radiation makes a substance radioactive. So, you know, this maybe comes from cartoons or something, but someone gets hit by a beam and then they start to glow green. That's not how it works. You need to actually have radioisotopes in you or on you in order for that material to be radioactive. So if you're able to remove radioisotopes, which we often can do, then the exposed substance will be totally clean. It's not going to be radioactive for the rest of its life. So, for example, if we were able to make a product with uranium, some polymer or something, it wouldn't need to be radioactive forever if you can get the uranium out there. So that might pose a challenge for your catalysis, but it's an important thing to keep in mind. So there's just a few myths. And then this is just another beautiful video that I wanted to show, sort of showing what's so just showing like some of what I get to do on a daily basis. So I have this reactor in my flask. What you're seeing here is actually the growth of product crystals in the flask that are then getting so heavy that they fall off of the sink from the interface down into a pile of crystals below. I just thought that was a really neat image because, yeah, a lot of what I do is try to make new compounds and crystallize them, which is typically a symbol of purity, and then do further chemistry with those. So these crystals are a beautiful yellow color. And yeah, so I used the compound from this reaction to discover a new catalytic reaction with uranium. And so that was pretty exciting for me. And then, yeah, I think at that point, I want to just give sort of my outlook on uranium's future. So my understanding is that the radioactive problems we have today are here to stay. This waste that we have generated, these weapons that we've generated, they're going to be radioactive probably longer than human history. So we need to be thinking now and forever about how we're going to handle these. We can't just say, it's too scary, we can't touch it, or anything like that. We need to be working on these problems actively. I also put Richard Butler's axiom of proliferation here, which is the idea that as long as one state has nuclear weapons, other states are going to try to get them, basically. And so there's not an obvious way in which we can just have a world without nuclear weapons. Of course, it's a constant policy struggle. But these are problems, yeah, that we really need to be thinking about right now. How do we implement safeguards to prevent disaster? How do we make sure that people are not weaponizing the materials that they have? How do we make sure that weaponizable material isn't getting into the hands of bad actors, into new states? So this can happen at the policy level, like the International Atomic Energy Agency, which routinely inspects refineries all over the world. And it can happen at the technological level, like what I was showing you earlier with the spectra that I take, developing new methods for imaging and detection to make sure that even if someone's not reporting what they have, we're able to figure out that things are leaking out or moving around. And then how do we make something good out of this element's history? Can we really reliably and sustainably handle this for good applications? So that's where I'd like to finish up. Some ideas for further reading here if you're interested in any parts of this process, or I can try to do something else if you want something more technical. But yeah, at this point, happy to take any questions.
Thank you, and for showing us all the things that we're doing today. My question is, I wanted to delineate the threats from actually weaponizing or using a byproduct to just simply having nuclear power. There's of course so much NIMBYism about it, but I mean, since Russia's most recent invasion of Ukraine, there's so many headlines of how close something was to hitting a nuclear plant and what that would do. So I guess first, could you say exactly what would happen, or what is the? Because you're talking about removing uranium to prevent radioaction happening. Can you tell like what are these things that we're supposed to be so afraid of with every news from the war front there, and also like what possible way is there to safeguard nuclear power as we use it now?
Yeah, these are big questions. So let me make sure I'm understanding your first question right, is sort of what should we be afraid of, maybe in?
Well, I just don't really understand more than the catch-all of like, oh, another Chernobyl. Like, I don't understand what is literally going to happen
Mm.
when we talk about the threats of getting a bomb in a nuclear plant.
So, yeah, I mean, that's one of the challenges is trying to be as creative as the bad actors who are out there or trying to predict bad things that could potentially happen. So, you know, Chernobyl happened, 3 Mile Island happened, and we may have thought, okay, we got this figured out. And then Fukushima happened, right? So it's hard to predict in some ways the things that can go wrong. That said, at this point, I think there's a lot of unwarranted fear about nuclear power. Because with responsible use and with some of the new technology that's, you know, been developed in the last 20 years, it can really reliably and safely be used. But yeah, I mean, if Russia were to you know, demolish that power plant, that would of course be a huge radiological disaster that, you know, we haven't really seen before. But it's a tough question of how a state could weaponize. I guess the question is maybe still a little broad for me, but yeah, did that answer it at all, or?
Okay, yeah, that could be multiple things. But I mean, could there technically be like? Sorry, no, my question is like.
Okay, yeah, I'm happy to try to just chat about it, yeah.
You're talking about nuclear security and like how we can
Yeah,
better
like
protect
they're
the.
trying to. At the last moment, you have to take uranium out of a certain plant to like move it away from the path of.
Contingency plan, okay, fail safe and then.
Yeah.
Take that.
Yeah, I mean, certainly the situation in Ukraine, I think, would have been hard, you know, even if the loss of that territory had been foreseen, it would have been hard to plan for. Because, yeah, there's a lot of challenges with moving this material around. There are all kinds of controls that you can implement to prevent different sorts of disasters. And I think that's what I refer to when I say that, like, in the last 20 years, I think we've come a long way in some of the engineering controls that we have to prevent things like 3 Mile Island or Fukushima from happening. You know, for example, in some of the next generation reactors, if the core starts getting too hot, it will melt some substance that immediately buries it. That's going to prevent some of the cascade of activity. But yeah, you know, predicting geopolitical events like an invasion, that brings a whole new element of uncertainty and challenge. Yeah.
I hate to be the one to build upon more uncertainty, but when it comes down to older generation power plants that have been decommissioned, like the one at the USA that is underneath there and that was started up in the early '60s, how are they running amongst that power plant to make sure everything stays contained? Or if something was to happen to that, but I know the students half of the students don't even know that it's there, but yet they walk around and go like, I don't got no signal. But with that being said, again, do we have tactics for those older plants that we can implement now?
Retrofitting.
Yeah,
Yeah.
that's the exact word.
Yeah. Yeah, there are plans to retrofit a lot of the older reactors in the States. You know, encouraging other countries to do the same is, again, sort of a political challenge. But yeah, the US has plans to retrofit some of the old reactors. Yeah. Yes.
I guess I have kind of a question about like the nuclear fuel cycle.
Mhm.
How much of that is state controlled?
That's an interesting question. So it is sort of a commercial process. But which is a lot of the reason why certain parts of it don't happen in certain countries. So in the US, for example, this picture that I showed you way back here of the fuel cycle, wherever that, yeah. This is sort of an idealized picture, but some of these steps don't happen in the US. Like these really nice ideas of reprocessing and recycling, we don't do that. It just goes, it's a long-term place. Because they're expensive. So it is still a market-driven process. Of course, the US government has an extremely heavy hand in regulation and in safeguarding of its own. And that's for a number of reasons. That's for our own internal peace of mind, I guess. That's also for international safeguarding reasons. So the US and Russia, for example, have very direct and constant communication about the amount of material that they have at any given time. And then, you know, we are a participating country in the International Atomic Energy Agency. So we are routinely inspected by third parties as well. So it's in our best interest to keep a close eye on this, but it is still, yeah, it's a sort of a partnership between industry and the government. Yes.
I wondered, so I was really excited to see all your the forums that you've shown to it for fun, and I wondered, are there other groups other than Berkeley that are also interested in the chemistry you're in?
Yeah, definitely. So Berkeley has a really strong history in the chemistry of the actinides because of figures like Glenn Seaborg, who discovered plutonium, things like that. But yeah, there are groups all over the country and all over the world that research this. There are, you know, we have our own oversight. You know, we have Cal OSHA watching over us, and they have OSHA watching over them. So there is infrastructure that needs to be in place in order for a university to work with Uranium. Like, you know, you can't just buy it off eBay and start doing chemistry with it, at least not legally. So not every program does it because of those sort of bureaucratic barriers. But yeah, there are good research institutions all across the country that do it. Yeah, I mean, I could give a list if you're interested, or yeah.
It's been really interesting to learn. Thank you.
Yeah. Yeah.
So a nuclear power plant can never be shut down unless it goes critical or something bad happens. It has to stay going.
No, it can be decommissioned.
We can.
Yeah.
Okay.
Mhm. Yeah, absolutely. So California is decommissioned and it's
Okay.
yeah. So yeah, I mean the fuel rods that you use, there are different ways to control the rate of the nuclear reaction that's going on in there. If you want, you can slow and stop that process and then remove the rods. You put them underwater, you cool them down, and then over time you're able to phase out that reactor. Mhm.
Over time.
Yeah. Probably not going to happen overnight, but
Yeah.
What's like an especially cool compound that you think you might be able to make from uranium, where essentially is, I guess maybe as like a secondary question, do you envision like the ultimate way of carrying out your research as being based on like the waste of a plant, or do you kind of think that like the nuclear power side of things is kind of a completely almost parallel, non-overlapping universe with the chemistry of uranium universe?
oh no, they definitely overlap. Man, the coolest compounds, I'd have to think about that for a while. I find, you know, most new compounds of uranium interesting for different reasons, but no, there's definitely a lot of overlap between what we try to do and the hopes for better treatment of waste. Yeah, that answers your question.
Thanks.
So your work, does it fit into one of the cycles with that from application side or your interest of the cycles you're showing here?
Yeah, so the way that I split up my work into two parts, focus one of sort of safeguarding, that would be more in the, we would be looking more at the fabricated fuels or maybe the spent fuels. So we're looking at small pieces of those materials and trying to figure out where did this come from or how was it processed, how did it burn, and things like that. And then the second focus of just trying to get uranium to do new types of chemistry is not, I would say, related to the fuel cycle that much at all. We're just looking for new ways to use this element productively.
And well, like some of the work help with like clean up the disasters, like in the humans, the radiation or uranium in the human body, you will be able to use the compounds to kind of flush it out.
Not the compounds that I make, but definitely that's one of the many areas I think of like stewardship that is ongoing. So both how to get it out of bodies and how to get it out of the environment, which are sort of separate problems.
Okay.
But yeah.
So how you're working on how do you get it out of the environment in a way or not?
No, more part of the safeguarding component. So if material shows up in some foreign country where it's not supposed to be, right? It's not a declared nuclear state. We want to figure out, where did this come from? Could they get it from? Where was this milled? Stuff like that. My work is more on part of that investigation kind of side. And less on like environmental cleanup. Does that make sense?
Okay. Yeah, and so in order to figure it out, you will have to have all the signatures of are you looking at ore itself or the concentrated uranium?
It can be all kinds of, in any sort of chemical form. So any part of this process really, what I was doing was looking at fuel pellets most recently, but it can be any part of the process. And it's sort of like forensics. So we're looking at what's in there. A lot of it comes down to that, elemental composition. So, the ore that comes out of Kazakhstan looks very different from the ore that comes out of Canada. So if you can get elemental composition, then you're already part of the way there and figuring out where something came from.
Even if it's purified is like 99% or 99.999% all uranium. What kind of signature you might be able to get from that kind of concentrated uranium, that kind of purity?
Well, if you use a technique that's sensitive enough, then you'll still be able to figure out what that 0.001% is. So, so there are absolutely methods that are sensitive enough to, see the iron that you used to cut that thing with the grinder, for example. So, using the right method, you can still learn a lot, even when something is fuel grade.
Are there any questions on Zoom?
Let's thank our speaker once again.
Thank you, Rajiv and Joe. If you're interested